for different types of parameters. So here perhaps this is not well seen. When beta is near to 1, then you have something like normal distribution. The central limit theorem of probability works in this case. You get something very near to normal distribution. So it's very smooth. Yeah? When beta is very near to 1, then you get a very thin normal distribution and you get only values near to 1/2. But if you go with beta to larger values, you have this appearance, you have positive functions, but they become fractal. They are not smooth anymore. And then, if you go further and you cross the golden mean at 1.6, then you get this appearance and you have many zeros here. But still, you have only countably many zeros. But later, when you still go more to the left, to higher beta and smaller t, then you get Cantor sets of zeros. And this is very interesting. You see, here we have a function. I don't know whether it is continuous, but I would conjecture it is continuous. I cannot prove it. Yeah? Nobody can prove it. It has a Cantor set of zeros, but of course, in the numerical approximation, I take here 2,000 points in black and 50,000 points in gray. Yeah? We cannot reach 0. Yeah? The numerical realization will not give the zeros. Yeah? But we can prove we have Cantor set, and the Cantor set gets higher and higher dimension, and the dimension of the zeros goes to 1. At the same time, the distribution goes to the Lebesgue measure. Very strange. Yeah. This is the different types. So we have various appearances, and now there are some work, and Erdős was the first to have a substantial result, which is working up to today. As a young man, he was only 20 and something, yeah. He proved that for certain parameters we have no density. So we have a singular measure. And people were very much shocked. And up to now they try to see which of these values, which of the parameters are singular and which are regular, absolutely continuous with a density. And it's up to now it's not so. The situation is like that. For so-called piezo numbers, piezo parameters beta between 1 and 2, we have no density. And these are all the numbers where we really know that there is no density. Yeah. So since Erdős, nobody has found another example of singular. Yeah.
I do not remember what piezo number is.
Yeah, piezo I wrote there. It's a root of an integer polynomial. Yeah. A polynomial with integer coefficients, and all the other roots, the conjugates, have modulus smaller one. So the typical example of a piezo number is the golden mean, tau equal to root 5 plus 1 over 2. Yeah. And you know perhaps that when you take the golden mean to a power like 100, yeah, then you have always an integer up to 30 decimals or 50 decimals. Yeah. So these are relatives of integers. Piezo numbers are relatives of integers because their powers are all very near to integers. This can be easily proved. But we do not today, up to today, we do not know any other examples. Then there was some result by Garcia, and I don't want to define Garcia numbers now, but it's a similar family. And he proves that for those Garcia numbers, we have a density. And up to now, no other examples are known where we really have a density. But Boris Solomyak, he proved that at least we have a density for Lebesgue almost all parameters.
Let me make a short comment. Sorry, I apologize. He is my friend and my classmate.
Ah, oh. That too here. Yeah. I met Boris on so many conferences, and we have good relation. And he's really, I think this is the best result in the whole field, that we have the Lebesgue almost all points have a density. It's really very hard work, and it was published in Annals of Mathematics in 1995, and there are other papers now also, more recent papers. He's still working on this field. And Schmerkin is a student of Solomyak in Argentina, and he is most active in this field also. And they have proved with Hoffman in Israel that the exceptions have Hausdorff dimension 0. But I think Solomyak's result is the best.
What does it say? What does it say? Can you compare with the previous result of Erdős? Yes, what is it?
It says, Erdős says, when we take a Piso number, we have no density.
Yes.
Solomyak says, when we have a random parameter, then with probability 1, almost surely, yeah, we will have a density. Yeah. So for probabilists, the problem is solved. Yeah. Because we always have a random parameter. Yeah. But when you want to know whether it is true for 1.5, for instance, you don't know today. So this is very strange. Yeah. Oh, sorry. So now let me contrast this with the numerical reality. So here we see the Cantor sets, and I took still smaller parameters, and you see the Cantor set of zeros, which is also proved by Solomyak. We will also see that later. And it says that we have a fractal appearance, a rather singular appearance anyway. For all parameters, we have a fractal appearance. Yeah. We have no nice density functions here. But on the other side, when you look at the Piso realization, and I make a realization with 50,000 points here, yeah, you see it's very harmless. Where are the singularities? I don't see them. I think they go to infinity, yeah, but they go only up to 2. Yeah. And if I want to have values, you see this is a histogram of a measure. You can always do a histogram, yeah, by putting things into small intervals and just taking the measures of the intervals. Yeah. So here we have 50,000 intervals in the gray case and 2,000 in the black case, and we see the histogram. And the biggest value is 2.3, something like that. One can localize it for the. So the numerical reality is interesting. It's harmless. And most people have not done this. It's I think my pictures here are new. Nobody has cared for the numerical side. Can we recognize singular measures by computer? Can we recognize them from the approximation, say with 1 million pieces? Here I have 2.5 million bins, and I have 50,000. It goes only from 0.4 up to 0.5. I have 50,000 in blue and 2.5 million in red, and of course this is compressed. And you see this is a normal density. It's just a continuous function probably. It's not Hölder continuous, so it's also Hölder continuous, but with small exponent. It's not differentiable certainly, but it's harmless. This is the appearance for Piso number, another Piso number, not the golden mean. And you see here when you increase the resolution, you will have higher values and also smaller values. And the variation will be almost the same on the. When you take neighboring values, they are very far from each other. And then there is something. This is a Perron number, I have dealt with Perron numbers which are not like piezo, and you have a weaker type of singularity, you can prove you have peaks. You have a dense set of poles, which is indicated by the arrows, yeah, but you don't have a singularity. I think I cannot prove that it is non-singular, but this is a typical, say, L2 function with infinite values. Yeah. It's on this level of resolution, it has only values from 0 up to 3, but if you increase resolution to 10 to the minus 12, say, it will have values up to 7 or 10. Yeah. And it may go, this can be expressed by local dimension. Yeah. So it's, I think it is interesting also to see the numerical side of the singular measures, yeah, and have an idea what is the character of such functions. Because in mathematics we usually don't have an idea of those functions, a geometrical idea. We say, okay, this is L2, and there's my point, this is a function here. Or we say, okay, we have an integral, and this integral must be finite, but it's also good to have a picture. So there is some connection with some big data problems nowadays. And for instance, you have this very simple picture of air pollution data series, yeah, hourly data for several years, and you have also a fractal measure. Yeah. And so there is also an application potential. I just want to mention that when we consider Bernoulli convolutions and their approximation, and we want to characterize them by certain properties, we have an application potential to big data. But now let's come to the two-dimensional approach. I want to reformulate Solomyak's theorem and come to a more, to study